Today we will start with conformal field theory, but there is still a small part of chapter 6, repetition from last year, essentially categorical structures, which is missing, so that I will do first. Before that, just a comment. As you, Jürgen pointed out, I claim that this morphism in a category, in a topological category, which is graded, that this has the properties of a Rückenquist. This is not necessarily true. I think one can prove it indicates that the category is semi-simple. But in any case, I will not use that. So that's not conclusion. So the part that I still have to do is about Frobenius algebras. It's 602. This is a real definition now. We assume that C is a monoidal category. And then we say an object A in C is a Frobenius algebra. And only if it's an algebra. So I had morphisms mu and eta satisfying the relevant properties. It's also a co-algebra. Co-product and co-unit. And remember, we have this graphical description of the product, of the unit, and similarly the product and co-unit. And then there is a compatibility condition, which can, in graphs, be written like that. Conceptually, this means that with a natural definition of algebra on the tensor product of A with itself, the co-product is a morphism of algebras. It's a morphism of bimodules. And where A has the natural structure of bimodule over itself with the product as the action. I should also mention that of these two equalities, only one is independent, provided one uses all the other structure. And it's a nice exercise to prove that. It's not extremely hard to do it graphically, but you have to think like that. Then let me mention there's an equivalent. Two equivalent definitions. One is that there exists morphism, which I call kappa, from A tensor A to the monoidal unit. I will graphically represent it this way, such that it is invariant, meaning that if I compose it on one side with a product, I get the same morphism if I get on the other side. And in addition, it is non-degenerate in the sense that there exists a morphism from 1 to A tensor A, which is side inverse to this morphism, namely, if I propose morphisms in this way or in this way, then I get the identity. And actually, last year I think I gave a graphical proof of that. The thing is simply that if you have such morphisms, then, for example, you can get a candidate co-product by looking at this morphism, and then you show by using the properties that is is the same as this one. And from this, you can then conclude that this morphism is actually a co-associative co-product, and also you upload it. And the other way around is that you define your kappa to be the composition of product and co-unit. There's yet another evolution definition which I didn't give last time. Because it's very similar to what we have here, namely there is morphism which is sometimes called a Frobenius form, which is a morphism from A to 1, and I call it lambda. Such that and our wrote this only in the case that C is a duality. We require that if I use this symbol here for lambda, and then I require this morphism from A to A is invertible. And the relation to kappa is by composing this with the product here, such a bilinear form. One nice property of Frobenius algebras is any morphism of Frobenius algebras which simply means that it's an algebra and co-algebra morphism. Is in fact an isomorphism. And let me give a graphical proof of that. Now it's very simple. You just give the inverse. Assume we have such a morphism F between Frobenius algebras A and B. We need a candidate for the inverse. It should be a morphism from B to A. And there's a simple way to get such a morphism. Actually, two simple ways which are equivalent. Just compose these with the product and co-unit of B and the co-product and unit of A. Then you get a morphism from B to A. And you easily check by using that F is a morphism of algebras, respectively of co-algebras, that is left and right inverse there. This. Then last thing I did not mention last time, which is also very easy, but it's important for simplifying some proofs. It's the following statement. The A module, defined it last time, for a Frobenius is also a co-module. And again, this is easily seen graphically. What we need is a morphism from That's called the module M. From M to, say, if we talk about left modules, to A tensor M. And what we already know is that there's an action homomorphism from A tensor M to M. And now we compose those just here. Co-product and unit, and then you for checking that this is indeed a co-action, what you have to do is to show that this is the same as co-acting ones, and then compose with the co-products, and that you show simply by this single representation property to bring these two together, and then you use Frobenius to and assert coercive and coercitivity to complicate this picture. And also it has to be compatible with the co-unit, but that is also clear if you put the co-unit here, and the co-unit property just leaves you the unit here, and then the unit property leaves you the identity. A consequence of this is that actually the induction functor in the case of a Frobenius algebra is a two-sided adjoint to the forgetful functor. So we have the forgetful functor U from A mod C, and the induction functor which sends an object X to A tensor X endowed with the action given by new multiplication times identity on X. And we have seen that this is a left adjoint. So we have seen but here we have used just properties of the action and the algebra structure. Now, if we instead would use co-algebra and co-action, then instead of a left adjoint, all arrows will be in opposite directions. We will get a right adjoint, and therefore from this it follows that actually also interaction with the right adjoint. Indeed, I think it is true, but I have never proven it myself, and I do not quite know, but this is in the literature that this goes also in the other direction. If I have an algebra and co-algebra such that the induction functor is a two-sided adjoint to the forgetful functor, then actually the algebra has a structure of a Frobenius algebra. Let me just mention very briefly in one line as a remark that these statements that are now on the blackboard have counterparts for the categories. Remember that in the Categorical category, I have two tensor products, two natural monoidal structures. And if one now analyzes what one should call a Frobenius algebra in the Categorical category, One could say it's a monoidal category, so we have this definition, but it turns out this is then not a good definition. Rather, one should define co-algebra with the other tensor products than for the algebra, and then one has a definition of Frobenius algebra, which is analogous to the one I have shown, except that I cannot draw these pictures directly. Remember, the pictures I draw are always for strict monoidal categories, and I could rewrite everything in formulas, including the associator, in a unique way. In the Categorical case, in addition to the associator, we also need this left and right unit, left and right distributors, and since they are not isomorphisms, it's not guaranteed that things will work, but actually they do. Then again, something I have not mentioned in any detail, done some further definitions for Frobenius algebras. Now, in the sense I find. I think A is the Frobenius algebra. And we say that A is, some people call it coupled, some people call it connected. The connected one has the problem that sometimes it's also used for something else. So, for example, in the case of Hopf algebras, haploid has the disadvantage that it's not a very common term otherwise in mathematics. This means that base of morphisms from A is in a linear category. Linear homomorphic K is isomorphic, or is isomorphic to K. Then I call it separable. This actually I can define just for an algebra. If the product has a one-sided joint, a one-sided inverse. Let's simplify as something like this. So what I require is that if I compose this particular morphism with the product, then against the identity, and one calls a delta separable, or if one wants to avoid the symbol, one could also say co-multiplication or co-product separable. If it's separable, this particular morphism given by the co-product means we have this equality. Actually, one can show that under some mild conditions, which I don't remember, separable is almost same as delta separable, namely in this morphism that has to exist can then be derived by being the co-product together with acting with one particular invertible element on one of the lines. But we will not need that. And then there's enough special, and I will use it in this term. Some people call this normalized special. If it's delta separable, and in addition, special. if co-unit after unit is some number times the identity on one, where the number is invertible. And in the situation that the category is pivotal, or maybe circle, and here the safe side of circle, then I can actually use this theta here to be dimension of A, and then I call this normalized special. But some people call it a normalized special, but I will just use special. And then finally, if C is pivotal, and I call F symmetric. If and only if the following identity holds, so we have A here, and here we have A dual. This on the left side, we just have a duality here. Here I need the inverse of the pivotal structure to A here, and then A dual here. Let me see. Write this correctly. I have A here, then here I have A double. Yes. Yeah. So this here is, here I have what I call the co-evaluation for A, here I have the co-evaluation. So much about this addition. And now we come to a new concept example, which is about conformal field theory and related topics. And the first part of this will be about chiral. I will abbreviate conformal field theory by CFT, chiral CFT, and vertex support. I should say right away, I'm absolutely no expert on vertex operator algebras. We have an expert here in the room, and then I will also have to say something about conformal blocks, where Yongchang is much more an expert than I could ever be. But I will try to give you some impression of these quantities. But first, let's ask what is a conformal field theory? And the answer to this question is it's a bad question. Conformal field theory is a concept coming from physics, and there are no definitions in physics, so I cannot give you a definition of conformal field theory. Even there is a famous paper by Atiyah called The Definition of Conformal Field Theory. But this is one definition of one type of conformal field theory, and actually it's not completely trivial to describe that. Anyhow, let's narrow down this a bit. So it should be in some sense a quantum field theory. So some people also call this conformal quantum field. Which again is a term which is not which has not a unique definition, but in any case there should be some notion of quantum fields or fields or field operators in certain settings, and they are living or defined on some manifold, which physicists like to call space-time. Actually, in the application that we will have, if I have a metric, it will be a frequency signature, and then just call this space. But these are just names. What is more important is when people talk about conformal field theory in the context I will describe, when it's always meant in full dimension. Let's call this space here sigma, and then we consider the case that a sigma is as a real manifold as dimension S dimension 2. And so in short, it's a surface, and then is what is called a conformal manifold. Has a conformal structure. The conformal structure, I will write this in words, is an equivalence class of metrics, where the equivalence relation is multiplying the metric by a position-dependent factor, which is called conformal factor. And so one also says an equivalence class with respect to local rescalings. So just like you can just scale globally some say some subset of a manifold. Now you do this locally with different factors. Then another question is, what is the signature? When there are two dimensions, we can have a Lorentzian signature, 1,1, or Euclidean 2,0. There are approaches to conformal field theory which are in the which assume Lorentzian sigma. They, for me, have the disadvantage in the first place. They do not work for higher genus surfaces, and actually also not on the sphere, but only on the plane, say. And that's not what I want to consider. And also, in the existing approaches, largely one is restricted to unitary theories. I haven't really defined unitary, but there is a notion of unitarity for monoidal category. And this is a restriction that is important in certain applications, but I will refrain from making it, except if I have time at the end, I will say something about those cases. So we assume the Euclidean, and also we assume the world will be compact. And actually, indeed, for a compact two-manifold, on a compact two-manifold, there is no Minkowski metric except that the genus is one torus, not on any other compact surface. And this is partly for technical reasons. One way to think about this is that I can insert fields. What that precisely means, we have to understand. But this somehow means that on my manifold, locally I cut out a small disk and give some data. And then this involves in particular a local coordinate around some point here. And since the manifold is conformal, I can apply conformal transformations to modify this. And I can, for example, do it in such a way that I'll add a very long cylinder here. And then this is I can describe situations where I have in the spirit from field theory fields incoming from minus infinity and outgoing to plus infinity, even though I actually work compact. I should mention that to some extent, surprisingly, if you reduce those approaches in the Minkowskian setting to their categorical aspects and just ignore that you require unitarity, then in many respects you get the same structures that we will encounter here in the Euclidean case. And there are even constructions of maybe vertex algebras, or at least some large part of it starting from that setting. But I have no idea how they work, so I cannot say more than just what I said. And an important additional, I will typically call these surfaces and worldsheets. This is a terminology borrowed from string theory, where you look at the one-dimensional string moving around in some ambient manifold and then sweeping out a two-dimensional surface. And in particular, when I say worldsheet, Euclidean and compact will be implicit. There is now one important distinction between two types of conformal field theories, which both, to some extent, are described in this way. I will be more precise soon. There is a distinction between what is called chiral CFT and what is called full CFT. The terminology full has been invented some 25 years ago in order to say not chiral. Previously, people were talking about these things but had no name for it. Nowadays, I think it's a more or less accepted term, even though it doesn't say really much. One could also say local conformal field theory or then full local, and we will see what that means. But for the moment, we will not talk about this in detail. And for quite some time, I will talk about chiral CFT. In this case, we are using the following information. We also assume that sigma is oriented, and not only that, but we choose an orientation and then a conformal structure together with an orientation. It gives one a complex structure. So for the purposes of chiral conformal field theory, I can write this also as an ideal with a complex manifold of dimension 1, or also says a complex curve. And in the case of full CFT, we will often deal actually with oriented surfaces, but they might be not oriented or even unorientable. So then one indeed cannot use this setting that I will not now describe. It will turn out that in order to describe full CFT, one has to know quite a lot about chiral CFT, and that's the reason why I did that first, even though I will essentially be interested in full stuff. And if we stick to prime CFC, there are important applications. One is in algebraic geometry, for example, what considerations that lead to what's called the Verlinde formula, which we will encounter a bit later, and in condensed matter physics, there are systems which sometimes are called spiral electron fluids. So phases of matter with certain property, like what you have in what is called a quantum Hall system, where it's really highly conformal theory that is relevant. But if we, as we will see, if we really want to talk about a quantum field theory in the traditional meaning of quantum field theory, then it will be full conformal field theory. But as I said, now we concentrate for some time on the Cairo case. And this brings us to the vertex operator alpha, about which I have already said I'm not an expert. So I will not give you any formal definitions here, but just some impression. And actually, the precise definition of a vertex operator algebra, several versions even, but no matter what version you take, is slightly complicated. In fact, if you want to, there are of course many sources, but one old paper by De Concini and Katz starts with a quotation which they assigned to Gelfand, saying that in a seminar talk or after a seminar talk, he said, "I'm an old man and I know that a definition cannot be so complicated." Of course, this is not fair because actually the definition of vertex operator algebra dating back to Borges was invented to make concrete ideas from physics. What is called operator product expansion, for example, in physics, and these are complicated things. And whatever you invent to formalize them, it cannot possibly be too simple. So very concretely, even in the book by Katz on vertex operator algebras, he more or less states that the axioms of vertex algebra are the same as what is called Weidmann axioms in quantum field theory. I strongly oppose to this view, but they are at least in the same spirit. So this is really something strongly inspired by certain structure. So I will not give you a definition, but some aspects of the definition. I will denote the vertex algebra maybe always by V, and this will involve the following data. First, a complex vector space, which I also call V, and then what is called a field map. Robert, if I say anything wrong, please correct me, yes? So this is a linear map from, let's call it Y, from the tensor product over C of V with itself to V with this symbol here, where Z is some formal variable. And this notation here means that I talk about the raw polynomials. So a power series in Z and Z inverse, which are bounded below. And then there is a, well, somewhat unexpected but convenient notation. One writes Y of AB, where A and B are elements of my vector space, in the following form. Y of A and Z applied to B, where the formal variable that comes from nowhere is here explicitly stated in the notation, and then also in terms of the dependence on Z, one writes this as sum over all integers A and B Z to the power minus n minus 1. That is here is a convention which is the mathematical convention in physics. Sometimes some use a different one, where here this is a kind of a product for any given integer of A with B, or an action of A on B. And that in short, if I forget it now about the B which I add, that means I say Y of AZ is a sum over n of A n Z to the power n minus 1, which is an element of the endomorphisms of V with arbitrary power series in general in Z and Z. Where by definition then An is an element of the endomorphisms of V, meaning I can apply it to an element in V, and I require, in order to be compatible with the restriction that I have here, that for any fixed, I don't have enough space here. For any vector V in V, An applied to V is 0 for n sufficiently large. Among the data, often one includes more, but I will not do this now, but definitely later. So, in a minute or two. I will not write down the axioms, but let me just mention that they are a bit complicated, and they somehow can be or look like the axioms that you have for a unital associative, commutative associative algebra. And it's only roughly like that. Of course, it's something much more complicated, and the complications come from the presence of this formal variable. In fact, on the other hand, any unital commutative associative algebra is an example for a vertex algebra. A trivial one, but it is. And in particular, that means there's a unit element which is denoted by this symbol here, which in physics is sometimes called used for the vacuum state in the quantity theory, and I forgot one important thing. It's a derivation. And then we call the derivation D, and then the terms include, in particular, that if I use this, it's sometimes called vertex operator, so the field map corresponding to this particular element, and apply it to any element A, I get back A. And if I apply y of A and Z to 0, then I get A plus something which contains at least 1 power of this formal variable set. And finally, for the derivation, one has the formula and computes with y and z up to the derivative with z. And what I forgot to say is that I said here formal variables. There are rules for working with formal variables. And I will not say anything about them, but they are not always what you would naively maybe guess. So we have to be careful when working with them. In particular, when you not only have one formal variable but several ones, then you have to distinguish between power series in one variable, which in addition are coefficients of a power series in the other variable, or power series at the same time in both of them. Okay, time for a break. And then after the break, we'll start with the relation, the term conformal and vertex conformal. Other questions?
So what's your reason for opposing Kant's view on the viewing vertex hydra as a Weissenbach theory?
That's not my of opposing, or
yeah, opposing.
Well, the point we'll see this later. What we have described is not a quantum field theory in the sense that you have correlation functions as people discuss in ordinary quantum. Rather, we have what is called conformal blocks, and those I will talk about. If you accept, as many both mathematicians and physicists do, to think of conformal blocks or spaces of conformal blocks still as correlators, then it roughly amounts to it. But I wouldn't want to do that. But I don't mind too much if others do. So, to continue, in the definition of vertex operator algebra, some people include the following datum, some not, and then call including it by a slightly different name. But let me just, for example, conformal vertex algebra. I require that there is what I sometimes call the conformal vector, denoted by omega, such that the corresponding field y of omega and z, which I now denote by a slightly different convention. I call the Laurent coefficients Ln, but the Laurent coefficients which take the right only as z minus n minus 2. And then if I do that, then these Laurent coefficients Ln should satisfy the relations of the Virasoro algebra, Virasoro B algebra. So the commutator or the Lie bracket of element n and n is given by n minus n L n plus n plus 1/12 n to the third minus m times c, where c is a central element. In the case, if I regard this just as a Lie algebra, but for a given vertex algebra, the central element is represented or is given by a fixed complex number times the identity. In addition, the mode L minus 1 coincides with the derivation D. Sometimes one also requires that these linear maps, that the linear map L0 is diagonalizable, but this restricts the number of models one can look at, and it can be generalized, so I will not write it down. In any case, what one gets in the presence of such a conformal vector, I should also say in physics, this field is often called the energy momentum tensor or energy momentum field, and some people call L0 then also a Hamilton operator. Again, this is in the spirit of identifying vertex operator algebras and quantum field theory. But I will not use that term. So from this, it follows that there is set grading on this vector space V, and V can be written direct sum of subspaces N with Vn consisting of those vectors in V such that L0 on V equals N times V. And as a side remark, instead, here we use this formal variable set, and we will actually see later that this is a very sensible thing to do if you want to make contact with conformal field theory, because we will then think or identify this with local holomorphic coordinates, but there is also a coordinate independent description. Via the notion of a kind of algebra. Independent mathematicians, this is this term for something completely different. So this is Beilinson and Grünfeld, and modules. But I will not say anything about that, except that this is more general. You can define these things for arbitrary smooth algebraic curves, and in the case that the curve is actually the affine line, you get back vertex operator by choosing such a formal variable. So much. That's all I want to say about vertex operator algebras themselves. Next, about representations. Since morally the vertex operator algebra is an algebra, even though not formally an associative algebra, one would say that there's an unblock of representations, and indeed one can give the following definition of a B module. This is a pair consisting of a vector space W, complex vector space, and some map YW, where YW is analogous Y. So it's map from the tensor product of V and W to W, but with to the space of Laurent polynomials, values in W. And that this is compatible with the axioms of V, and compatible in the same sense as we define compatibility, the action of an algebra, except that now that things are more complicated and I don't write down any formulas. Now, important here is that for generic vertex operator algebra, the classification of modules is very hard or impossible, but there are often specific types of modules, restrictions one can impose, and then one can get under suitable conditions a nice category of modules. So the objects are the modules, and the morphisms are suitable intertwined. Not only that, there's one easy a module that we always have, namely the vertex algebra itself, just like the regular representation of an algebra. One can also ask, is there a tensor product of representations? And indeed, one can define what is called sometimes a fusion product of representations, giving a monoidal structure on the category of V modules, where the monoidal unit is just V itself. Under certain conditions, one can define this. Now, we have already encountered one way of defining tensor product modules, namely we had a tensor product over R from bimodules over a ring. In the commutative case, this gives us a tensor product modules. and the tensor product here is somehow in the spirit of that. So this is in contrast to the tensor product of modules over Hopf algebra, where you do not have to take a quotient of the object you start with, but you can use the co-multiplication to define the action on the tensor on that object. Now, crucial ingredient to define this is a bilinear map from a pair of modules W1, W2, W3. And we will think of this as a linear map, which I denote by the script Y here, from W1 tensor over C, W2 to W3, and now it turns out that Laurent series are not enough. Rather, the first cited here, here one allows in principle for arbitrary power series. There are in concrete cases then restrictions actually, but in full generality it's that. And in addition, these can also be polynomials in a new formal variable. Which is called log z, because one has to require that BTZ of log z is 1%. So if we have something there, then we get an intertwining operator. From W1 tensor over C W2 to what we will then call W1 tensor over V. So this is the fusion product W2 with this dependence on Z and log Z, such that this satisfies the universality property. But this is the way I define that. For any intertwining operator I of the form that I start from tensor product over C, and I get an arbitrary module X, say, that is the corresponding power series in X elements. This is now I, and then I have this Y, W1, W2, this tensor product. Such that there exists a unique morphism in intertwiner from this tensor product. So this must exist and be unique. just like for other universal properties, if this is the case, then my fusion product is determined uniquely up to unique isomorphism. But then, of course, also like with often with universal properties, it's not easy to make this concrete for a given vertex algebra and its representations. But I will not talk about that, but just claim or tell you that four suitable classes, large classes of vertex algebras. When I say vertex algebra, I use it synonymously with vertex operator algebra. As I said, there are various conventions in the literature. For some people, these are defined differently. So for a large class, vertex operator algebras and some properties of that I might mention later. We have such a fusion product, and in addition, I have a grading, a balancing, this, and also rigid structure. And I should say right away, rigidity is the hard thing to get, such that V mod becomes a written category. And in those cases, for example, I already said the monoidal unit, vertex algebra itself, together with the field map. Then, for example, the left unit constraint. And we describe as follows. Its component at y and this intertwiner y and w. So this is the unit. It's the unit of a z w is just given by the field map for y. For a z applied to w, and the associator can be described as follows. Not entirely precise, but still lengthy. If I look at its component at w, w prime, w double prime, then applied to the intertwiner for w and w prime, tensor over v with w double prime. For an element W in W and the formal variable Z applied to the element obtained by looking at the intertwiner for W prime, W double prime, for W prime, Z prime, now applied to W double prime. And then there is certainly a preferencing. But this is the same thing as the intertwiner for the other order of tensoring, W prime, and then W prime applied to Y W prime of W, and now Z minus Z prime. Apply to W prime and this is Y W prime. And the non-trivial thing here is that in this case you have power series in Z prime as coefficients in a power series in Z. Whereas here you have power series in Z minus Z prime, and you must relate them by the rules of for formal variables.
I think the difficulty here is that you cannot do it using formal variables. You have to do it with complex amounts.
Yes, yeah, okay, yeah, yeah.
Complex.
So formal variables, as long as you have products, so on this side, it's okay, I think.
Yeah, on both sides.
Yeah, but Z minus Z prime,
Yeah.
you can write, you can interpret as Z times 1 minus Z prime over Z, or differently, and
I think you expand that won't necessarily knowledge into a series, and that is that primes that exactly agrees with
okay.
left side. So you have to do, it has to be, they agree up to some kind of a continuation.
Okay, yeah, yeah, yeah. Yes, actually, I had a remark here, but I will not, it doesn't add. And actually finding associators which satisfy that is the main obstruction to a fusion product to exist. If it does exist, then one can describe a grading of swallows. Component X, W and W prime. Calculating this way, this should be W prime and W. On the element here is obtained from the one for W prime. Now variable minus that, and analogous issues then here by applying here equal to Z times the -1 component of the reserve element. So remember, this was the same as the derivation that we have on the algebra, and this can actually be understood now in terms of complex coordinates. If we think of that on the real axis, say the minus Z will be here, and then this vector here can be seen as moving along a half circle about 0, where 0 is the location of W prime. Where I have Z prime equal to 0. Maybe and then the twist is theta at W is essentially just taking e to the 2 pi I 0 acting on W. Now I said the most tricky part, apart from the existence of non structure, but if you have it among the written structure aspects, rigidity is the most tricky part. And I just want to mention one thing. If I consider V star, which is the grade-wise dual. And here, for example, I can look at situations where these graded components of V are all finite dimensional, and then this is just a dual of a finite dimensional vector space, and then this makes sense. This is always the V module. And for rigidity, one needs that this is actually isomorphic as V module to 1. In under general conditions called C1 cofiniteness of the vertex operator algebra. One has a generalization of that. V star, and then acts as a dualizing object in the sense of particular particle. So under this condition, one has not reached but still could be. Now, C1 cofinite is a property which I will now define, and there is a quite a bit more restricted property I also will now define called C2 cofiniteness. One can show that if a vertex alpha prime is C2 cofinite, then actually a tensor product exists, and V mod is not just a monoidal category. No, sorry. We first say this V mod is a finite category in the sense I have defined, and then by V mod, one means a certain subclass of modules which are called admissible, which is the natural requirement on that and then. And if a vertex alpha prime is equal to cofinite and in addition semi-simple, meaning that this category is a semi-simple category, then V mod is even the non-Cartesian category. And in this case, the corresponding current conformal field theory is called the rational conformal field theory. And the origin of the term rational is a certain data, like logarithm of the twist eigenvalues are rational numbers, but actually that holds also beyond rational conformal field theory, so it's not a very a good term. And all I want to say in generality about modules. Next, I define the character of a V module as a formal power series in the first place, a chi W of some variable, which in the first place is a formal variable, as a trace in W over the linear homomorphism Q to the L0 minus C24, where C is this value of the central charge that is fixed, and Q is related to tau, or the other way around, and that Q is equal to pi tau. In the first place, this is a formal variable, but then for suitably nice ERAs, I can take the tau to be a complex number in the upper half plane. And get a conversion power series. In the particular case of a rational, let's call this a rational BRA. If V is rational, not enough space here. On the other side. then one can define the following transformation S, which sends chi omega of tau, now regarded as a variable in the upper half plane, complex number, to chi omega of minus 1 over tau, and T sending it to chi omega of tau 1. And then S and T generate a representation of the group SL2Z, a protective representation of the group SL2Z, which is the number group, the mapping class group. And this is actually not literally true in simple cases, so-called minimal models. This description defines what SLT are. For more general situations, one has to define characters not in this way, but has to introduce additional variables. So, for example, there are, I will talk about this later, vertex operator algebras associated with semi-simple Lie algebras, and then the Cartan angles of those Lie algebras have to be included in general. Now, this is the first part of a series of considerations which leads to what is often called the cylinder formula. And I will not give this as an actual formula as it's usually stated. I can do this later because I need some additional concepts. But one way to actually say this is that this S, which I get here as a matrix, then in the rational case, actually it turns out there are finitely many isomorphism classes with modules, so I can write that in terms of the characters of simple modules. I just get the square matrix S. Let's call this the S matrix I get from V, and that this is equal to the S matrix. Let me denote it this way: that I get from the category, the modular fusion category here. Remember, we have defined a matrix S by the trace to the trace of the double grading, and I indicate this in this way. Now, sometimes people say that the cylinder formula applies the amounts stating that the matrix that I get here actually. Maybe I can put tilde about this. There's a certain normalization factor, 1 over S goes 0, but that is easy to implement. Some people say that actually the cylinder formula means that the matrix S that I get from the double grading diagonalizes the fusion rules, and this is a statement which is correct, but it's much easier to prove than the actual statement that is relevant here, namely that this equals the S matrix coming from modular transformations of characters. And let me just indicate this before the break. I think it's nice to have seen this argument. We need some notation. So we have this set of isomorphism classes of simple objects which I have called capital lambda. And then I look at morphism spaces of the form that I take lambda prime, and say mu, and take alpha. Yeah. More say with basis alpha of this morphism space and the corresponding dual basis denoted by alpha bar of the morphism space in the other direction. And of course, I should have labels lambda prime and mu, but I suppress them. So what does this mean? Dual basis. It means that if I compose alpha bar with alpha prime, let's say, I have mu here. Mu is a simple object, and all of this is over complex numbers. So the morphism from mu to itself is just a one-dimensional vector space, and I have lambda prime here, and then I could choose a new prime here. It will be non-zero only if mu is prime, and with choice of dual basis, it's non-zero only if alpha is equal to alpha prime. And in addition, then there's a completeness relation, saying that if I sum alpha bar after alpha over all alpha, and then sum over all mu that I have for given lambda and lambda prime here. And this is just the identity on the kind of product. Lambda and lambda prime. Some of course this involves some convention. In condensed matter physics, actually, people include a factor of dimension of lambda very often here. But I prefer this. And then with this convention, and also abbreviating the coupons now by just small dots, one gets the following. I use small s for the unnormalized matrix up to a number. Then one and show this is a normalized one that by definition S is this trace. Where I have mu here, and then I use the definition again. One has to be slightly careful with the prefactor here, but this amounts to looking at this situation. So we have mu here and mu and lambda here. But then I use this completeness relation to replace the identity here on the tensor product by a sum over alpha. Alpha bar like this, and there should be some over what I had called mu there, but mu I have already used, so let's call it kappa. So kappa will have here. Now I can deform this by using the rules for rigid duality and well, the fact that the breaking is it's natural to identity we write this as this. Not wissen hier, then I have alpha and alpha bar here. But I know from the first relation that this is equal to 1. So what I get is the sum over kappa and then I have kappa and mu and then sum over alpha delta alpha alpha, which is nothing but what I have called diffusion coefficient 10 lambda lambda mu. So there's lambda and mu here in kappa. And that means that I can rewrite this here as sum over kappa and lambda kappa s kappa mu. And this I can also rewrite in a different form, which I will write later, where I express by using the S effect, I can be chose to be unitary, and then I multiply. It's invertible in any case, I multiply with inverse, and I get a formula directly for these fusion rule coefficients. Okay, let's have a break now. Now we come to the issue of fields that we want to have for a quantum field theory in some way. So in our situation where we have this representations of some symmetry structure, which are vector spaces or states, as physicists can sometimes would say, then one would like to have sometimes called a state field from quantums. So a linear map which associates to any vector in one of these, say, vertex operator algebra modules, something we would call field I lambda, which depends on W, but also depends on P, where P will be a point in some manifold like the worldsheet or the corresponding complex curve that I have described. And then, in addition, a linear assignment where I suppress now the vectors here from sigma and the choice of points in abbreviated often by a P with a vector sign to something one calls a correlator, or would like to call a correlator. Already said that we have to be a bit careful here for this situation. So this will depend on sigma and on P and on lambda, where lambda stands for lambda 1 up to lambda n. And one, in addition, would like to think of this correlator as some kind of, this would say, expectation value or vacuum expectation value, where one has the field phi lambda 1 at position P1 in some way multiplied with phi lambda 2 at P2 and so on up to phi lambda n at the end. And now in a real quantum field theory, these correlators should be function of in particular the positions, and this of course will also depend on sigma, so it should also be a function of the variables that describe the shape of sigma, say the modular parameter tau of the torus. And this is something which in our present situation we do not have. We will, well, there's a natural guess one could make, namely in the case of a vertex algebra, we would simply say that these are our vertex operators. But that we would identify this as y w lambda for w and z. Z is now, however, a formal variable that is not quite the right thing. But we can, in order to relate it to this point P, we can try to interpret or think of Z as a local holomorphic coordinate on a little disk around the point P. But this is certainly something one can do. However, what one will get in this way, I will describe in a few minutes what one can do concretely, is not a correlator in this sense, but rather, let me put a tilde on it now, something I would not like to call a correlator, even though in literature often it is called a correlator. Some people then say chiral correlator. I prefer to call this a conformal block. And I have to say a bit more about what mathematically what a mathematical object that is. And there are actually several different related meanings of the term conformal. And I will mention most of them. So the first thing to notice is that the vertex algebra acts on W lambda, and I could say it acts locally, namely in terms of the formal variable Z, which I interpret as a local coordinate. And now it turns out that for suitable classes of vertex operator algebras, one can get a global chiral symmetry from that. On the tensor product, of the corresponding modules, and then one looks at invariance with respect to this vacuum. This amounts to linear differential equations with respect to these coordinates, and these are in by using a term borrowed from physics called the chiral Ward identity. And if I look at these differential equations, then I have vector spaces of solutions to these. And for nice vertex operator algebras, these are finite dimension. And in this case, or maybe also more generally, I call these bases of conformal blocks. Or the further space of chiral blocks, but that term is not used so often. And we denote this by EL for block. And this is a Roman B, index lambda for the labels of the modules, and then this will depend on the surface and on the positions. And I will now try to make this a bit more precise in 2 steps. In good generality, we have an expert in the room here, but I don't know much about this in the situation that the vertex operator algebra is not rational. And even in the rational case, I don't know the details except for some subclass, and those details I will mention to some extent. But one thing one does in any case is that we regard these block spaces as a linear form of the following, let's call it beta on this tensor product, W lambda. So that means we have beta really standing for beta depending on x, p, and lambda, an element of W lambda. Assuming that they are finite dimensional, so that we know your space. This is again be a finite dimensional vector space, and then we can think of these correlators here as this linear form applied to an element W1, W2, and so on, Wn in this tensor product space. Or in this would be the tensor product over C, and then we can project this to tensor product over V. And for general vertex operator algebra, this is still more like an idea than a prescription. But there is a class of vertex algebras where one can actually do this. And that I will describe. I should say that nowadays quite a bit more is known. There are ideas using bundles of vertex operator algebras, or a notion called chiral Lie algebras. And let me, I will not even try to define what this is. Let me just mention two recent preprints, and then there are references there to the literature. There's one by Damiolini and Voigt. And there's one by Hao from last week or so.
Yeah, I think so, maybe 2 weeks ago.
I cannot read what I wrote here, but something like that. And I will now only consider case I know more about. V is a vertex algebra which depends on two data. G here is a finite dimensional complex simple Lie algebra, or maybe semi-simple, but it's enough to look at a simple case. And L is, with suitable normalization convention, non-negative integer, a positive integer. And this particular class of vertex algebra is one which is generated in a suitable sense by what, again, from physics, occurrence. These are fields, so in the sense of the vertex operators Y, which have an expansion. Well, let me write maybe as Y of some small J and Z, and often one denotes it by capital JA, such that the zero Laurent modes of that, so it's GA 0, span the D algebra G, and more generally the JAN satisfy the relations of G1, which is the untwisted affine D algebra associated with G. So that can be described by looking at the group algebra. No, I should not write that here. Some variable E, say, and depending on what you're looking at, this might not be just polynomials, but some slightly more general power series, plus a central term, a central extension. And again, the central extension has a fixed value in the application to the vertex algebra, and this is this number L that is here. This is also called the level of the relevant representations of the affine D algebra. In conformal field theory, in physics context, one calls this also corresponding conformal field theory, a WCW model, where the first W and Z stand for Sumino, who have nothing to do with it, or essentially nothing. And W here is Witten, who formulated this in a Lagrangian formulation, which is a so-called sigma model on a group manifold, with adding a topological term, and that topological term is called the Sumino term. In the more representation theoretic approach, in which I would formulate this, this has been done by Knischnik and Samologikov. So understood what they are as conformal field theories in the sense that I will use later on. And in addition, also the energy momentum tensor, so this field corresponding to the conformal vector, is a quadratic expression in the JAs, namely just JA, JB, and then contracted with the Cartan-Killing form, and then normal ordered. And I don't want to tell you what normal ordering is. So this is not completely trivial, but it's something that you can describe easily. So in short, here you have such a conformal vector, but it's not something independent. You get it from this underlying currents or current algebra, and the Laurent modes of these satisfy the relations of an affine, untwisted affine Lie algebra, which is something well known. In particular, if what I assume here is level is a integer, then among the representations of the affine Lie algebra, there are the so-called integral representations, and it turns out that a nice class of modules over the vertex algebra precisely corresponds to those. And there are finitely many up to isomorphism, and it's one can say quite a lot about that. Now, in this case, the construction of this global action goes as follows. We first start with something which is sometimes called a global Lie algebra. One just takes, I don't have a name for it. One takes this finite dimensional Lie algebra and the tensor product with S sigma E, where this is the space of functions, complex functions which are holomorphic on sigma minus these points. And a closed finite order progress. Yes. Points pi. And then for each value of I from 1 to m, we associate to the zero mode, G0, and I will suppress the label A in the following. So this will just be everywhere. Tensor F, so this is an element of this space. Associates to this, the following A with index I of F, and sum over N, A, and I, with Jn, which is an element of the untwisted kappa B algebra, where these A and I's are defined by taking the function f and expanding it into a Laurent extension around the point pi and choosing some local coordinate, local holomorphic coordinate, which I call psi I. And then I get Laurent series, which looks like over AIN and CI, XII to the power n, and these are these A and I's that have to use here. And then one defines, the following defines an action of this global Lie algebra on tensor product W lambda. Given by summing over these i's from 1 to m, and then acting with the identity everywhere except the i's position. I take this ji of s, which I have defined here. So this is an element in the universal enveloping algebra of G1 to tensor power m, maybe up to some completion here, but I will not have. And I now have this action on tensor product, and one should maybe mention these individual modules of the affine algebra. On those central element acts non-trivially, and by this number L, but the corresponding term that I get when I sum here, because these are the summations of one and the same function f around all these points, this will add up to 0. And then one can define the space of blocks to be the invariance of of the dual space of this space with respect to the dualized action of what I have described here. Alternatively, one can work with co-invariance directly for this tensor product. Now, very briefly, otherwise I will not be able to cover what I want to cover. I have chosen local coordinates here. This is a choice. So if I make a different choice, I will get something different. But the different choices are actually related via conformal transformations. Well, provided that the vertex operator algebra is C2 cofinite, in any case, then just the Virasoro algebra provides a natural action of the group of coordinate changes. And the conformal blocks define this way the transform covariantly. So this was assuming that we have fixed this complex curve sigma and the positions pi on it. Now, in the next step, we can vary the position pi and also the moduli shape of sigma. And these actually correspond to a point in the moduli space of complex curves of a given genus and a given number of m of pairwise existing points on it. Actually, this is a small subspace of a larger moduli space until the GM, where I include local coordinates. Now it turns out, true in this case, but also in more general cases, that we get this way from the blocks a quasi-coherent tree on this extended moduli space. And in case that V is rational, then this descends to this small moduli space. I can ignore the local coordinates, and then these finite dimensional vector spaces we together form the total space of finite rank vector bundle. Similar by script BL G lambda on MGN. And the second use of the term conformal block is not for these individual fibers, which are finite dimensional vector spaces, but also for these vector bundles. And it also turns out that these bundles come equipped with projectively flat connection. It's homologic of a connection which come from a flat connection given by d plus L minus 1 tensor descent on vector bundle over MGM with phi 1 being it's a product vector space. No. With for one choice of E, choice of lambda. And from this, it follows that there is a projective action of the fundamental group of MGM, which is also known as the mapping class group. Of the surface sigma and of surfaces of given genus G and different distinct points on each of these vector spaces. So, for example, when sigma is the torus and there are no marked points, then this gives us present. And I only say this in words. Terminology compound block is used both for these vector spaces, then for these vector bundles, but then also for the use of local horizontal sections with respect to the homology of connection. And one thing important now for us in connection with conformal field theory is that these sheaves are generically non-trivial. So if I think of them as functions, they're not really functions, but multi-value, they have monochromies. And this is something we do not want to have in a actual quantum field theory, and therefore the Kuiper conformal field theory that we are considering so far is not yet what we, or at least in many applications, want to have. In addition to this, and I think I will be very short with this now. Again, in the rational case and to some extent beyond, but I'm not at all informed about that. One actually not only deals with vector bundles on MGM. When I said complex curve, technically I mean a smooth curve. It turns out that much of what I described can be extended from smooth curves to what is called stable curves. And for this one allows for some my type of singularity, which one might indicate as follows. So if this would be a curve without singularities, and here I have a singularity, but this can be, there's a process of blow up this singularity, which somehow amounts to adding a further dimension here, so that of this point where I have singularity, this is split into 2 points, and then this can be done in a nice way, and I will not talk about this at all, but the upshot of this is then that actually these bundles, we get bundles which I which I don't use a new notation over the modal space M GM and large GM of stable point curves. And in addition, there is relation called factorization of conformal blocks, namely the fibers are under these situations finite dimensional, and I have isomorphism between the situation that I have some surface with insertion points and the situation where I cut the surface into two. So I get this amounts to well, precisely what happens when I remove a singularity from the eye in the semi-simple case, and then I start with a block space for where I, in addition to my points here, I have two more points, P plus prime, say, and P minus prime, come to the resolution here. And for those, I have to include labels mu and mu bar. And mu bar is the label corresponding to the dual module. And then I have the space of blocks here, space of blocks for sigma prime and E together with these two additional points where I have these labels mu and mu bar. And sigma here is a curve with singularity. Sigma prime is the one that I get by blowing up. And effectively, then I have a system of vector bundles over all the moduli spaces of this type for all genera G and arbitrary number n. So I have relations among all of them. And next is some remarks. I have been making many words about the dependence on the blocks on these positions, and also local coordinates. Not on the dependence of on the choice of modules, but there is not much to say. Except for one word. This is factorial. So if I look at morphisms between modules, say the depends module substance is fits together with the action of the vertex algebra, and in the case I described for this for the simple Lie algebra, depending vertex operator algebras, just a consequence of the representation theory. And the second is for the non-rational finite, in the sense that the relevant, there is a representation category which is no longer modular fusion category, but still a non-semi-simple finite tensor category. One expects, or to some extent knows, you will know that, and that is relating here, it generalizes involving replacing the direct sum by a coend. And also this factorization is a crucial part in the proof of the actual Berliner formula. And I can now give you the full Berliner formula if I have time, otherwise I do it next time. So I leave some space here, because I want to mention also one other aspect, which is again important when I come to full conformal field theory. Yet another use of conformal block or space of conformal block is as a finite dimensional vector space endowed with an action of the mapping class group. And obeying factorization, what I just erased. And I don't write it down depending functorially on the representation theory labels. And this amounts to describing a block space as a morphism space in the category C of V-modules of now tensor product. Here this is tensor product of V, but I use the notation for a normal category just of representatives of the in this isomorphism classes of simple modules to one. This is what I get in the case of genus 0. If I have genus G, then that was an additional tensor factor L to the power G, where L is the direct in the semi-simple case, direct sum of 1 year equals 1 euro. Graphing case, and in finite case, this is the corresponding coend. One time is over, so I will not write this formula this time. One final comment. Now, I jump to board warning. A system of vector spaces with these properties gives also gives a structure called the model of functor. And the model of functor can be regarded as the two-dimensional case of a two-dimensional part of the three-dimensional topological field theory. Any model of fusion category, while the restriction derived construction gives you a three-dimensional topological field theory with a certain anomaly. And it's widely believed that the conformal blocks that I get in this way from the vertex operator algebra and the state spaces of that topological field theory associated to the same model of fusion category are actually isomorphic as finite dimensional vector spaces with these actions or with these properties. And this is for the this Wesseling-Witten case proven, I think. At least there's a paper which proves it and which is published very prominently. But I don't know anything about the details. So one has to be careful with that. And in particular, if one uses it beyond Wesseling-Witten, one should keep in mind that this is not proven, even though I would say everyone who knows anything about that is convinced that it's correct. Okay, that's a good point to stop for today.